In the next two videos, we're going to be looking at code generation for a language that's higher level than the simple stack machine language we've been talking about so far. So here's a language with integers and integer operations, and this is the grammar. So a program consists of a list of declarations. And what's a declaration? A declaration is a function definition, so it has a function name. The function takes a list of arguments, which are just identifiers, and the function has an expression, which is the body of the function. And what can function bodies look like? Well, the expressions can be integers, identifiers, if then else, and the only predicate that we're going to allow is an equality test between integers, and then sums of expressions, differences of expressions, and function calls. Now we'll just say that the first function definition in the list is the entry point. This will be the main routine, or the function that gets run when the program starts. And this language is expressive enough to write a Fibonacci function, and here it is. And it's just a standard definition. If x is 1, then the result is 0. If x is 2, the result is 1. Otherwise, it's the sum of fib of x minus 1 and fib of x minus 2. Now, to do code generation for this language, we need to generate code for each expression E. We need to produce MIPS code for each expression E that accomplishes two things. First of all, that code is going to compute the value of E and leave it in the accumulator A0. Right? So when the code for E is done, the value of E will be stored in the accumulator. And furthermore, the code for E, the generated code for E is going to preserve the stack pointer and the contents of the stack. That means whatever the stack is when we started executing E, or the code for E, the stack will be exactly the same after we're done executing the code for E. And we're going to write a code generation function, cgen of E, that produces code. Okay, so cgen of E is something that produces a program, it produces code that will accomplish these two things. Now our code generation function is just going to work by cases. And to begin with, let's focus on the expressions, and we're just going to have a different kind of code, or a certain kind of code that's generated for each kind of expression in the language. So to evaluate an expression which is just an integer constant, all we have to do is load that constant into the accumulator. So the code generation for I, for the constant I, is the instruction load immediate into the accumulator the value of I. And it's easy to see that this preserves the stack as required, so this doesn't modify the stack pointer or the contents of the stack at all, so the stack is exactly the same before and after the execution of this instruction. And another thing I want to point out, or I want to emphasize here, is I'm going to be following a convention that things that are in red are things that are done at compile time, and things that are in blue are things that are going to be done at runtime. So in this case, at compile time, we execute the function cgen of I, and that produces code here that will run at runtime. Okay, so cgen of I is something we execute at compile time, and it produces a program that will be executed at runtime. And this is to help you separate in your mind and develop a very firm grip on the idea that we have a real division of time in these programs. There's stuff that happens inside the compiler, and then there's computation that's deferred until the program that we're producing actually executes. All right, now let's look at another example. Let's take on the addition of two expressions and think about the code that gets generated for that. So what are we going to do? Well, the first thing that happens when we execute E1 plus E2 is we have to compute the values of the sub-expressions. We have to know what integers we're going to add. So we better generate code for E1, and that's going to happen at compile time. We're definitely going to generate that code at compile time. And then once we've got the value of E1, well, remember we only have a one register stack machine, so we're going to have to save that value somewhere until we also know the value of E2. And where are we going to put it? We'll do what we always do. We'll put it on the stack. So E1, the code for E1 is guaranteed to leave the value of E1 in the accumulator. So what we're going to do is after we've evaluated E1, we're going to store the value of the accumulator onto the stack. And we know how to do that. We store A0 onto the stack, and then we have to bump the stack pointer. And then we can generate code for E2. Okay, and again, this stuff in blue, this is part of the program that will be executed at runtime. These are calls to the code generator that are happening at compile time. Okay, And so we generate the code for E2, and that goes here after this code for pushing the value of E1 on the stack. And once we have the value for E2, now we can perform the add. So how do we do that? Well, first we retrieve the value of E1. So we load the value of E1, which is on the stack. And notice that this works because E2 is guaranteed, the code for E2 is guaranteed to preserve the stack. You know, this code for E2 here, and let me digress for a moment, this code for E2 can be arbitrarily complicated. This could be a whole program. It could go call functions. It could allocate data structures. It could print things out. It can do all kinds of complicated things. But because we have this invariant that all code generation for all expressions will preserve the stack, we know that no matter how complicated this is and how long it takes, when it's done executing, the stack will be in the same state. And that's what allows us to know where to find the value of E1 that we stored away. It's going to be at the top of the stack. Okay, so we load the value of E1 back into a temporary register. Now we can do the add. Okay, so we add T1 and A0 together and store that back in the accumulator. And now we have to pop the stack. And now notice that this is all the code here for E1 plus E2. And when we're done, we've established our two invariants. The value of E1 plus E2 is in the accumulator. That was established by this instruction. And this pop here restores the state of the stack. So now the state of the stack here is exactly what it was when we entered this block of code up here. Now, to be completely precise, I really should write this code generation function out a slightly different way, and that would be like this. So what we're really doing here is we're generating code for E1, and then we're printing out into a file or something like that the code to do the push, okay? And then we generate the code for E2, and now these calls to code generation are also printing into the same file. Okay, so here, you know, this has printed out the instructions, whatever the instructions are to execute E1. This is printing out the code to do the push. We print out the code to do E2, and then we print out the code to do the add and the pop. Yes, the add and the pop. Okay, and this is just this is much more verbose over here, and so I'm generally going to leave out the prints and just indicate in blue the instructions that are deferred. But I hope you understand what this means. Everything in red here, of course, is being done at compile time. So we're calling these code generation functions at compile time. The print statements are being executed at compile time, and then we're accumulating somewhere in some data structure or in a file all the instructions that will be executed at runtime. So let's think about a possible optimization to this code. Instead of pushing the result of E1 on the stack, what if we stored the result of E1 in a temporary register T1? What would the code for that look like? Well, in that world, to generate code for E1 plus E2, what would we do? We'd generate code for E1, and that would be followed now by, instead of pushing the result on the stack, we would take the result of E1, which of course is in the accumulator A0, and we would store it in a temporary register. And then we would generate code for E2. All right, that would be followed by the code for E2. And then we could just do the add. We would take the result of E2, which is in the accumulator A0, add it to the contents of T1, and store that into the accumulator A0. And of course, there's no pushing and popping from the stack here, so this code preserves the stack. And it looks like, anyway, that it actually puts the value of E1 plus E2 into the accumulator. Unfortunately, this code is incorrect, so this is actually wrong, and you don't want to do this. And to see why, let's consider what would happen if E2 was itself actually, let's do it for a concrete example. Let's do the example 1 plus 2 plus 3, parenthesized like that, okay? So what's going to happen? So E1 here, so we're doing 1 plus 2 plus 3. So this will be a load immediate. The code for E1 will be a load immediate into A0 of the number 1. Okay, and then we'll have the move. We'll try to save that value in temporary register T1. And now we're going to generate code for E2. And what's E2? Well, E2 is itself a plus expression, so we're going to recursively call the code generator to generate code for 2 plus 3. So we generate code for the new first expression. So that will be a load immediate into A0 of the value 2. And now you should be able to see what's going to go wrong, because since this uses the same code generation strategy, it's also going to try to use T1 to hold the temporary value. So it's going to move the accumulator into T1, thereby clobbering the value of the previous sub-expression that we had evaluated, the number 1. Okay, so that value is going to be overwritten. And then we're going to do an add. And oops, I made a mistake. We're not going to do an add. Let me erase that. Forgot to generate code for the 3. So now we load the value of 3 into the accumulator. And now we can do the add. Now comes the add. And so we do A0, T1, A0. And when you execute this, what do you get? You get 2 plus 3, which is 5, and that's fine. But now we have the value of this sub-expression in the accumulator, and now we're ready to do the outer add. And so that generates another add instruction, which is exactly the same. But unfortunately, the first value of T1, the first temporary we tried to store, has been overwritten. And so what's in T1 at this point is the value 2 instead of the value 1. And we get that 1 plus 2 plus 3 is equal to 7, which is not what we wanted. And so the problem here, of course, is that in the presence of nested expressions, and particularly nested expressions of the same kind, if the expressions try to use a fixed register for their temporary values, then if you try to generate a code for two different expressions that are nested, two expressions of the same kind that are nested inside of each other, they will step on each other's temporary intermediate results. And so that's why we have to use a stack to store intermediate values. So this example illustrates a couple of features of code generation that I just want to emphasize. First of all, notice that the code for plus is really a template that has holes in it for the code for evaluating E1 and E2. That is, there are some fixed instructions that we emit, and then there are places where we plug in the code for E1 and the code for E2. Okay, so that's what I mean by a template. So there's some fixed stuff, which are the instructions that actually do the add, and then there's a place where we can just plug directly in arbitrary code, whatever it is, for implementing E1 and E2. And we'll see this same pattern with all the other kinds of expressions. The other important point is that stack machine code generation is recursive. That is, the code for E1 plus E2 is code for E1 and E2 glued together, and recursively we generate code for E1 and E2 which will have their own templates. They may even be other expressions of the same kind, as we just saw. And what this means is that code generation can be written as a recursive descent of the abstract syntax tree, at least for the expressions. All right, so let's consider another new instruction. Let's add the subtraction instruction. And this is just like the addition instruction, so sub just subtracts two registers instead of adding them. And code generation then for a subtraction expression will, as you might imagine, look an awful lot like code generation for a plus expression. So what do we have? First, we have a place where we plug in the code for E1. Then we have to store the value of E1 on the stack. We have to remember that intermediate result. And then we can go off and compute the value of E2. So this is where the code for E2 gets plugged in. And then at the end, we load the value of E1 back into a temporary register, actually do the operation, the subtraction, and then pop the stack. And the thing to note about this code is that it's exactly the same as the code for addition, except for this instruction right here, where we do a subtraction instead of an add. So next we're going to talk about code generation for if-then-else expressions. And to do that, we're going to need some control flow instructions. So we'll need two, in fact. So here's the branch equal instruction. And this jumps to a label if the contents of two registers are equal. And then we'll also need an unconditional jump. So this just does an unconditional branch, not a branch, an unconditional jump to a particular assembly instruction. So now let's take a look at the code generation for the expression if E1 is equal to E2, then evaluate E3, otherwise evaluate E4. So first we have to evaluate the predicate, and in order to evaluate the predicate, we first have to evaluate E1. And by now, this pattern for binary operations should be familiar. So we evaluate the first sub-expression. We save the result on the stack, so we push it onto the stack. That takes two operations, one to save the result of the accumulator on the stack and the other to move the stack pointer. Then we evaluate E2. Now we've evaluated both of the arguments to the predicate. The result of E2 is in the accumulator, and the result of E1 is at the top of the stack because, again, the evaluation of E2 will preserve the stack. So now we load the value of E1 back into a temporary register, and we pop the stack. And then we can actually do the comparison. So now we do a branch equal. So if the value of E1 is equal to, this is actually the value of E2 in A0. If that's equal to the value of E1, then we branch to the true branch. Okay, and otherwise we're going to fall through if they're not equal. Okay, and so we'll call that the false branch. And what are we going to do if we fall through, if this test fails? Well, then we want to evaluate E4, and that will leave the value of E4 in the accumulator, and that will be the value of the entire if-then-else in the case where the predicate is false. So when we're done, we're going to branch now to some code that will just clean up and end the if statement. We'll see what that does in a moment. Otherwise, we still need to implement the true branch, so we'll stick the label for the true branch here. And what do we do on the true branch? Well, we just evaluate E3. Okay, and then the end if, well, actually there is no cleanup to do because E3 and E4 both preserve the stack and they leave the result of their expressions of the accumulator. So we reach end if on from E3 if we executed the true branch, and then in which case the value in the accumulator is the value of E3, and we reach end if through this branch if we executed the false branch. And then the value in the accumulator is the value of E4. And so this correctly implements an if-then-else expression.